Hey everybody. So today we're going to do the next two pages in our notes, which mostly focus on momentum and energy conservation. So we're going to be discussing the ideas from the first few problems that we did with momentum, and then combining it with the energy conservation stuff that we did before. So I wanted to start by showing you just this little video clip here of what's known as a ballistic pendulum. And so I've got this video here, and he's demonstrating it. And so what we have here is the little pendulum here hanging, and a little spring-loaded gun here that's going to fire this wooden ball on the end here. And then there's a little receiving hole here, so the wooden ball is going to get fired into this pendulum, and the pendulum's going to swing upward. And then this device here is going to catch the pendulum when it swings. So I'll just play the video so you can see it.
2, 1. Okay.
All right, and so here's a little close-up view of it again. So the ball was fired off of this spring-loaded. It went into here, and then this pendulum swung upward. So this is going to be kind of our example for what we look at when we're doing some of these momentum and conservation problems. So some of them follow this idea, but what you could see in that video was when the kinetic energy from that ball collided with the pendulum itself. The pendulum then took some of that velocity away from the ball. There was a inelastic collision. The ball and the pendulum stuck together after the collision and moved as one object upward. So there's principles of momentum conservation that we could look at there, but there's also principles of energy conservation that we can look at as the pendulum swung from a kinetic energy at the bottom, where it was moving the fastest, up to the max height where the kinetic energy was 0. So we had energy transfer as well. And actually, from doing this, we could determine the speed of the ball based on the height of the pendulum, something like this. And this is actually how you can test out muzzle speeds of particular rifles or other firearms by shooting into a block of material and having that block hanging and just measuring how high that block would swing backwards. And so this is the type of problems that we're going to look at today. So let's jump right in. I'm on page 6 here, and we'll look at the first example. So it says a bullet with a mass of 0.03 kilograms is moving at 250 meters per second. When it impacts and embeds itself within a wooden pendulum, which has a mass of 1.6 kilograms. So just to give an idea of what this picture would look like, here we have the pendulum hanging, something like this. The bullet is moving toward it, and this thing is at rest. This pendulum is at rest. This is moving with the speed of 250 meters per second. And they give us the mass of both these. This mass is 0.03 kilograms, and this mass is 1.6 kilograms. So that's the information they gave us. And they said after impact, the pendulum swings upward. What height will the pendulum reach after impact? So this is actually kind of a two-step problem. So we're going to look at this as being stage 1 here. And then stage 2 is going to be something like this. So stage 2 is going to be right after the collision. So right after the collision, the bullet is going to embed itself into the block. And now we're going to treat this as now one object, right? Our system is the block plus the bullet. The bullet was at rest, but now, the block was at rest, but now the bullet and the block have one velocity, which we are going to have to figure out what it is. And the combined mass is going to be the combined mass of the bullet and the block, 1.63 kilograms. And this I'm going to call point 2 of the problem. And before we can actually solve for the height, we're going to draw another picture and see that's 0.3. we're going to have to solve for this velocity. What does that allow us to do? Well, that allows us to get the kinetic energy. And once we get the kinetic energy, then we can use that to determine the height of the pendulum. So after this, the third picture here, the block would, the block would swing upwards. So let's draw it a little bit, swinging like this. Pretty bad. Fine. All right, the bullet's still embedded in there. And now it's swung up to its max height, and so now its velocity returns to 0. But what we want to look at is, let's say this was our original height here, where it was initially, and now we're trying to figure out what this height is here. And so this is what I would call it as picture 3. All right, so if you want to take a second and see if you could set up the equation for part 1 here, and we're going to basically go from part 1 to part 2 to solve for the velocity. So maybe pause the video and try and write down the equation that you think you would use for that part right there. Okay, so hopefully you gave that a try, and what you should have here is your initial momentum of the bullet, 0.03 times 250. Let's do this in another color. So mass times velocity of the bullet, plus mass times velocity of the block. Now the velocity of the block is 0. And so this is going to have no momentum. We can write it in though. And then on the final side of the equation, so this is your initial momentum right here, would be pi, and then equals, and then here's your P final. This combined mass, 1.63 or 1.60 plus 0.03. You want to write out the math. And then there's our V. And I'm going to subscript this as V2 because we denoted this picture as 2. And so this is obviously a 0. You can multiply these together, divide by the 1.63, and you're going to get a V2 equal to 4.6 meters per second. And you got to use this number here to solve now for the energy part. So this part was going from 1 to 2. We used momentum conservation. Now we have to go from 2 to 3 using energy conservation. And this is similar to what we did in last chapter. So from 2 to 3, you notice we have at the bottom here, now we know what this velocity is, 4.6. And so now we have kinetic energy. This thing has a height of 0, doesn't have any potential energy, or at least we're going to say that that height is 0. And then that means it has potential energy at the end once it swings up and reaches a velocity of 0. So on the left-hand side, we just have kinetic energy, or Ke. And on the right-hand side, we just have gravitational potential energy, PEG. So 1/2 mv squared equals mgh. We can cancel the m's. All right, V we're going to plug in as 4.6. So we have 1/2 times 4.6 squared equals 9.8 times RH. So multiply 4.6 or square 4.6 and then divide it by 2, then divide by 9.8. And solving that out gives the H value of 1.08 meters. All right, and that's all there is to it. All right, so in this problem, it's a little bit different than what we just did, but it has a similar feel or similar theme to it in terms of like there's 3 different stages that we're going to be going through. In this one, we're kind of going in reverse order than the last one. So it says we're standing underneath a small suspended 1.5 kilogram block. We throw a piece of clay up at it. Clay is 2.2 kilograms. The clay sticks to the box and both move upward after impact, reaching a maximum height of 85 centimeters. How fast was the clay moving immediately before impacting the box? So essentially, block, well, doesn't matter. It could be an elephant and it wouldn't matter. So here's our block hanging, or our elephant being suspended from the ceiling. And we throw something at said elephant or said block or said box, like a lump of clay. And that clay is going to, it's going to have an inelastic collision. It's going to stick to the block. And this is going to cause these two objects to move upward with a certain speed. What we know about this is that after the collision, this thing heads upward until it hits rest. And the height that it reached, if I look at this here as the height, is 0.85 meters, or 85 centimeters. So the goal here is I want to figure out how fast the clay was moving before impacting the box. So I actually have to go one step further back, because here it's already impacted the box. So just like we had before, this I'm going to call stage 2. This I'm going to call stage 3, but we actually haven't drawn the picture for stage 1. The picture for stage 1 simply looks like this. Very similar to the picture from stage 2, except the clay has not yet collided with the box. And I'm going to call this V1. And this is the velocity of the clay. V2 is the velocity of the clay and the block after impact. So our goal in the problem is actually to figure out the impact or the velocity before impact at V1. But in order to do that, if we want to do a momentum conservation problem between here and here, where we have an object colliding with another object, we need to know what V2 is. And in order to get V2, we have to use energy conservation. So it's a similar practice to what we did last problem, except now we're going in reverse. We're going to go from 3 to 2, and then from 2 to 1. All right, so let's start with looking at 3 to 2. So we have over here, we have potential energy. So this will be my final side. And in part 2, we have kinetic energy, but no potential. So this will be my KE initial. So I've got the 1/2 mv2 squared on the left-hand side. And this should equal the mass of the block plus the clay that's on there, GH. So here the masses cancel because we're talking about the same mass. We're talking about the combined mass of both objects. V2 is what we're solving for. G is 9.8. Height is 0.85. So we get this equation where we can solve for V2. And V2 we should get to be 4.08 meters per second. So simple enough. Energy conservation. Now we know, okay, so once the clay impacted the block, it was moving up at 4.08 meters per second. So how fast was the clay moving in order to make the box and the clay move at 4.08 meters? It must have been moving faster. And so now we look at kind of the second part to this as, kind of from 2 to 1. It doesn't matter if I write 1 to 2 or 2 to 1, but the idea here is we're going in reverse order, which is why I'm writing them like that. But we're really looking at what is the momentum at point 1, what's the momentum at point 2. Whereas here we did energy conservation between 2 and 3. Here we're looking at momentum. And basically the rule of thumb is how do I know, okay, Mr. Sherrick, how do I know when I should use energy versus momentum conservation? Because that's kind of the tricky part of setting up these problems. Well, You know, because it'll tell you the height in when there's a change in height, and that means the energy has changed. Momentum has nothing to do with height. Momentum is just velocity. And so in this case, there's no change in height from 1 to 2. So we're just looking at the momentum conservation of this collision. Generally, momentum is going to be dealing with a collision of some sort. So we know we can use momentum between 1 and 2, energy conservation between 2 and 3. So the momentum here between 2 and 1 would be, let's see, we'd have this small mass of the clay, 2.2, moving at some velocity, which we called v1. This is just the velocity of the clay plus the momentum of the block. Now the block is at rest, so it's not going to have any momentum, but we can still write it in. But we just know that this term is going to go away. And then after the collision, so at point 2, it has this velocity of v2, but the masses have combined. So now we're looking at 2.2 plus 1.5. The mass is stuck together. So that's our total mass, and our velocity is 4.08, which we solved in part 1 of this problem. So multiply these all together, divide by 2.2, and solve this. You'll get a velocity of 6.86 meters per second. And again, a sanity check here. Is your velocity greater before the collision than after the collision? Should be, since this thing obviously is going to be slowing down. Throw something into another object. It's not going to gain more speed. So there you have it. All right, so that's example number 2. So let's look at our third example here. And this one is, again, somewhat similar to this first example, but we're going to add in spring energy now. So we're going to look at what happens if we, instead of having a pendulum, we attach a block to a spring or something like that and absorb the energy that way. Right? Basically, what was happening, we were absorbing the energy in the block in terms of potential gravitation. Now let's see what happens if, let's say, we absorb the energy with a spring. So similar setup, we have the bullet traveling 350 meters per second, and it collides and embeds itself in a wooden block, 3 kilograms. Here we have 0.02 kilograms. Here we have 3 kilograms. And they collide. And this is at rest against an uncompressed spring. So it is just chilling. Our spring compression is 0, all that. Just as a reminder, you might need this equation for this problem. PE spring is 1/2 kx squared. Okay, we're going to use that, where x is delta x, amount of compression or stretchiness. Here we're looking for how much the spring will compress after the impact. So the idea is, again, 3 stages. Stage 1, bullet moving by itself toward the object. Stage 2, this is after the impact, but before the spring is compressed at all. So here the bullet embeds itself. We get a combined mass of 3.02, but the spring is still uncompressed. But now it's got another velocity, which we don't know, which we've been referring to as v2. This here would be v1 of just the bullet. This would be v1 of the block, which is 0. And then finally, our third picture is the spring compressing. So the block slides a little bit, and the spring is compressed, absorbing that energy into the spring. And we can see now delta x, which is the amount of spring compression, is the variable that we're looking for. And what we know is when it's at max compression, velocity goes back to 0. So again, we're going to look at energy conservation between parts 2 and 3. And then we're going to use momentum conservation between parts 1 and 2. All right, now in this question, we're looking for delta x, so we're going to start and we're going to go down the problem this way. In the last example, we went from 3 to 2 and then 2 to 1. Now we're going to go from 1 to 2, 2 to 3. Start with the one that you know the most information about. Here we know all the information to solve this. From 1 to 2, namely, we have the initial velocity, and we're looking for this final velocity. So from 1 to 2, this again, we're going to now use momentum. Why not energy? Well, there's no change in height, and in this case, no change in the compression of the spring from here to here. Delta x is 0 in both cases. Why can't we use energy conservation? Well, the idea behind energy conservation is that when we have a collision that's inelastic like this, there's going to be energy loss. But there's no momentum loss, and this is key. There's no momentum loss because this is a closed, isolated system. But there can still be energy loss in terms of friction, in terms of the interaction between the objects. When you have a bullet colliding with something, there's a lot of energy transfer going on within that, and within that, there's going to be some energy loss. And so we can't use energy conservation, but we can use momentum conservation. From 2 to 3, you can use energy conservation because the object isn't changing shape in any way. But from 1 to 2, the block is obviously changing shapes because now it has a bullet. All right, from 1 to 2, we have our momentum here of 0.02, a velocity of 350, and here you have your momentum of 0. So, I mean, if you want to write this again, I like writing it just to show you that it is 0. And that's your initial momentum. And then your final momentum is going to be here with both objects combined, 3.02, with some velocity, which we call v2. All right, so, quickly plug that into your calculator, solve it, get 2.32 meters per second. And these problems should start to feel pretty familiar now. So now we go from part 2 to 3 using energy conservation, which we talked about. Here we're going to use energy. What is it? R, not an N, I think. Now we go here. What type of energy does it have? You said kinetic energy. You are correct. It's moving at some speed. What type of energy does it have here? You said spring potential. You would be correct. All right, so now we just go ahead and plug in our two equations. 1/2 mv squared. And this again is v2 we're using here. And 1/2 kx squared. K is given in the problem, 1800 newtons per meter. So that's important to know. All right, mass, we can't cancel out because there's no mass in the spring conservation problem. Just depends on the spring constant. So we do have to make sure we get the correct mass. Should I use 3? Should I use 0.02? Or should I use 3.02? So hopefully you said I should use 3.02. I feel like I'm making a Dora the Explorer video. Just pause, wait for you to answer. What's the mass? Oh, look, last day. Anyway, V2 is 2.32 squared. Here we get 1800, okay, and delta x. And again, I write delta x or x, it means the same thing. It's our amount that our spring is being compressed. So here you want to solve the left-hand side all out, multiply by 2, divide by 1800, then finally take the square root. And this will give you a compression length of 0.09 meters or 9 centimeters. And that is your answer for that one. All right, so I'm going to wrap today up with that final problem, and we'll do page 7 tomorrow. So we'll get a few more examples of this to work out, and then next week I'll give you a chance to do some of these examples on your